All right, today we're going to talk about motion in a different way. We're going to talk about calculating motion and how you calculate motion. So we'll start with speed. I think speed is a pretty simple concept to start with. It describes how fast something is moving. We talk about speed in our lives all the time. Not a difficult concept to understand. So let's talk about different ways we talk about speed. Regular speed, you can talk about how fast something's going. But you can also talk about the distance something travels in a given time. And we call that average speed. So how far do they go in a certain amount of time? You can tell about how fast they were going the whole time, but you can't tell exactly how fast they were going at each moment. So which car has more speed here? One drove 90 kilometers in 2 hours. One drove 100 kilometers in 2 hours. Obviously, car 2 is going faster in general. All right, average speed. So how do we calculate average speed? Easy. It's the distance divided by the amount of time it takes to go that distance. That is going to be your average speed. Easy formula. Distance divided by time. So S equals D divided by T. And here we go with our little special thing here. You cover the one you're looking for, and it gives you the formula to determine that thing. So we cover distance. Distance equals speed times time. Cover speed. Speed equals distance divided by time. Cover up the time here if that's what we're looking for, and that is our distance divided by our speed. So we can easily find whatever we are looking for when it comes to speed. Also, another concept, very simple, velocity. This is almost the exact same thing as speed, only we're talking about a certain direction. So I might go north, south, east, or west. I might go left or right, whatever, but a velocity must contain a direction. Same formula, only we have a V here instead of an S. Everything else works the same way. So we can cover to find what we're looking for. It is only, once again, a speed that tells us what direction we're going in. Velocity equals distance divided by time, right? We have to have our velocity. We do that in meters per second because it is our distance in meters divided by our time in seconds. Meters per second. Very simple. So velocity. Here we go. We got two different cars. They're going to the same place, but this car along the bottom traveled in two separate velocities, two separate speeds and directions, and then this car traveled in only one velocity. That is the difference. It tells us the directions we're going in. Right, so one car clearly traveled much further to get from point A to point B. Right, 16 plus 12, that's 28. This guy only traveled 20, so if they get there at the same time, one guy must have been going faster on average. And let's remember when we are doing our division. Our numerator goes on top, our denominator goes on the bottom. And when we set it up with our division little house here, the numerator is inside the house, the denominator is outside the house. We are dividing the numerator by the denominator. The numerator divided by the denominator. 5 divided by 12 equals, that is how we say it. Numerator divided by the denominator. That is how it works. Please get this right when you speak. It is necessary so that people understand what you're saying when you're talking about division. We are doing a lot of division here with speed and velocity as well as acceleration, so we need to get this right. All right, so when we talk about speed, we talk about velocity. We're talking about two different kinds of measurements. You have your scalar measurement, which is a speed. It does not contain a direction. We call it scalar. It does not contain a direction. It is merely a scale. And we talk about vector, something that does contain a direction. In math, you may learn about vectors, different directions, different parts of a graph, things like that, so you know where you're going. We've talked about quadrants, I'm sure, in math, the 4 quadrants of a graph, and that way you can tell a direction, a vector. So something that's vector contains a direction, such as velocity. Easy to remember. Scalar, speed, they both start with S. Speed does not have a direction. Vector, velocity, they both start with V. And you can make a little arrow out of your V telling you that there's a direction. Vector contains a direction. Very simple. It's just how we talk about things. All right, so let's talk about acceleration. Clearly, when we accelerate, we are changing our velocity. So acceleration involves figuring out the change in velocity. And we can see that right here. It's the change in velocity over time. Okay, we got a little bit different formula. Acceleration here, v2 minus v1. v2 is obviously your ending velocity, your second velocity. v1 being your beginning velocity. That's in parentheses because you have to do that first before you start dividing by time. So this is another way to figure out your change in velocity over a specific period of time. How much does your velocity change? How are you accelerating? This is the formula. This is how you figure it out when given two velocities. That is what you can do. Now, we don't have an easy little trick like we did otherwise, but it's just simple algebra. So you write down your formula. You plug in what you know, whether you know the acceleration, you know one of the velocities or both of the velocities, you know the time, you don't know the time. Write out your equation, plug in what you know, and then solve it. Simple, basic algebra. So, it's the rate of velocity changes over time. A lot of us think about acceleration like this guy here. He's stopped. We think of acceleration from stopped to motion. But acceleration can be more things. You can change from 20 meters per second to 30 meters per second. You can change from 30 meters per second to 10 meters per second. Any change in your velocity shows some kind of acceleration. Once again, acceleration equals your final velocity minus your initial velocity divided by time. Velocity here, both of these are in parentheses, which means you must do that first before you divide by time. Follow your steps just like algebra, because that's what it is. All right, so let's talk about reading a graph, because that's going to be important as far as motion is concerned. That way we can show motion on a graph, show changes in motion, many things. So looking at this graph here, if we've got speed right here, this is how fast something's going, and this is the amount of time, so we can show changes in speed. Which two cars, 1, 2, 3, and 4, have zero acceleration? Which ones don't change their speed? Right? That's easy to identify here because a straight line shows, right, if this is speed, the speed has not changed for cars 2 and cars 3. We need to be able to read a graph. We are going to practice that multiple times. So, as a ball accelerates, what has to change? Acceleration. What does it involve? It involves velocity, right? It involves time, right? Acceleration. So, what has to change? Does the mass change? Well, no. Inertia? Inertia is the, the likelihood of it staying still. Does the velocity change? Well, absolutely. The velocity has to change in order for the ball to accelerate. That's the definition of acceleration, change in velocity. Does the force acting on the ball have to change? Well, we know that the motion of things change when the force changes. So yes, the velocity must change and the force acting on the ball must change. So what do you have to do to accelerate a ball? Well, a net force must be applied. You could remove some weight. Friction coefficient must be reduced. It's got to contain momentum. All these things are going on, right? We're not likely to remove weight in order to accelerate something, but with gravity and its effect on weight, that is a plausible scenario. Not likely, but plausible, right? If we reduce friction, we're going to accelerate. We're going to go faster. That's why we lubricate things, so they move faster. We've talked about momentum before. Okay, a quick review because we're going to work with the equation here. So momentum, it's the force you have because you're in motion. We've done this before. Momentum we use P for momentum, equals mass times velocity. Very simple. Simple multiplication, right? Mass times velocity. Higher mass, it's going to give you more momentum. Higher velocity, it's going to give you more momentum. Very simple. Talked about it before. So if momentum, the equation includes velocity, it must be a vector quantity. It's a vector quantity because it has a direction, right? It includes velocity. We have absolutely talked about the conservation of momentum, right? When things collide into each other, that momentum is conserved. It goes somewhere. It's transferred from object to object. Here we go. Boom. Right? Transferring that momentum. Here the cars crash. You got your little explosion because they transfer momentum to each other. Here, with less friction, the momentum is transferred, and these guys go off in different directions with the same momentum. It is conserved. Here we go. So you got a larger object, so who's going to get most of it? Absolutely. The smaller object is going to receive a lot of that momentum because one object is clearly more massive. Same thing here, only obviously if it's even smaller, even less mass, it's going to get that momentum, and that momentum is going to affect it even more greatly because it takes less energy to accelerate a smaller mass. Therefore, all that momentum, that is some energy, transferring from a massive object to a much less massive object. You transfer that momentum, and that less massive object is going to accelerate more quickly. But all the momentum is conserved. Alright, so let's look at some distance versus time graphs, motion. So we're talking about a graph that shows us distance and how that distance is changing over time. If distance is changing over time, something must be in motion. So we're looking at the speed of a car. So which car had a constant speed? Well, we can see that this car traveled the same distance during every time period. If it travels the same distance during every time period, it is clearly going at a constant speed. Whereas this car changed its speed. It went at a constant speed for this, and then we're changing our speed, and we're changing our speed again. If we're traveling a greater distance in a shorter amount of time, that means we must have increased our speed, which means for number 2 here, obviously car 2 has accelerated. It has changed its velocity or changed its speed. Which car is going faster on average? Well, clearly the car that gets there first, right? That makes every bit of sense. So on average, car 2 traveled faster because it got there first. Took it less time to go the same distance. Got there first. And which car drove farther after 1 hour? Well, this obviously car 1 drove further, but then after 6 hours, clearly it was car 2. So we need to be able to read and see what is going on. This is the amount of time it takes us, and this is the distance we're going in that time. Same thing here. Looking at average speed, so we're doing distance divided by time, right? At point A, it has gone 5 minutes. It has gone 10 meters. That is distance divided by time. 10 divided by 5 gives us 2 meters per minute. 2 meters per minute. And then it goes, obviously, at the exact same speed. So we know from 10 to 20 is another 10. It's another 5 seconds. 10 divided by 5 still equals 2 meters per minute. And here we go. This one's doing much different things. Okay, this is Kyle on his bicycle trip, right? And his distances. Okay, during which 5-minute interval did Kyle achieve the greatest average speed? Well, that's going to be our slope, right? Here's a 5-minute period where he went 2 full kilometers because we go from 1 to 3. That is clearly going to be the fastest speed, right? And between 10 and 15 minutes, what happens? His distance didn't change. What does that have to mean? Absolutely, it has to mean that he stopped. All right, so we need to absolutely be able to read distance and time graphs. What happened to our distance over a certain amount of time?